Welcome to Temple of Pwn, Part 8. Today we're going to talk about keep the ball rolling with heap exploitation and talk about the unsafe unlink or the heap unlink, just kind of how unlink works in general with what it is and how it works in general with heap. Yeah. So it's mostly going to be with unsorted bins. I think it also works with small bins, but I didn't test it to make sure that was accurate or not. It should though. So as we know, there are chunks that are larger than fast bins get put in the unsorted bin list. The doubly linked list, and it's stored in the arena, are the beginning pointers. And then off to the right, we have the image that we've seen before about how the heap structure of a free chunk looks. So we have the size with the previous M-mapped allocated arena bit set. We have the forward and backward pointer, and then if it's a large chunk, the forward size and next back size. That doesn't matter for us today. And then the previous size, and then on the next slide I have an example of what it actually looks like. So here's this one, the middle image. We have the size, so this chunk is 110 bytes, 110 hex bytes plus the 1 to say it's in use, or the previous is in use. The forward pointer, the previous pointer, and then the previous size, so it's talking about this one's size, and then there's technically the next chunk. So this is kind of just to show an example of kind of what a heap scenario might look like. So we allocate a chunk A, this one's A, have some padding in between so they don't consolidate right away when we free them. There's B, B is right here, here's C, and then we just free them. And I have this printf just so I could break. But we see that after we free A and B, this is what our unsorted bin list will be. It'll be A first, which is right here, B second, and if we look at the forward and backward pointers, we see that A's forward pointer points to A0, which is the forward would be B because that's the next one on the list. And then its backward pointer points back to the arena where the beginning pointer points. And if we check B's, we can kind of see the same thing. The forward pointer points back to the arena, and then the backward pointer points back to A. So this is kind of what we're going to kind of abuse. So what unlinking is that it occurs during consolidation or the merging of two or more contiguous free chunks that are of correct or believable sizes, I'll say. So it won't really matter if they're free fast bins because they won't look to be freed, so they won't be consolidated. And then it's also used to reclaim freed space by a process, so it just makes the two chunks become one giant chunk, so we're able to allocate something large enough that could fit into the two chunks, which if they were separate, they wouldn't fit. And it's done with these two main operations. The current chunk, or like the chunk that's being consolidated, back's forward pointer gets set to the current thing's forward pointer, and then the current chunk's forward pointer's back pointer gets put to the current chunk's back pointer. And it might look a little funky, but if we kind of come back through here and look through it, that's saying that we'll follow A's forward pointer and then set its back pointer to A's forward back pointer. So like kind of just make sure that the chunks are synchronized if we're freeing it. So I don't have a good example, but if A was the only chunk here, this would also be the arena pointer. So I could just say that we're going to set the A's forward pointer to the back pointer, so it's just saying the arena to itself, saying that there's no more unsorted bin list chunks. And then we can abuse this by exploitation, since the backward forward, so if we have a use after free, we might be able to overwrite the backward and the forward pointers. So this kind of allows us to get an arbitrary write because we're able to control what gets set into this backward, or where it's at, and then kind of what gets set there because we control the forward and the backward pointers. There's only one restriction really, or one main restriction, is that the backward forward pointer has to equal P, or the forward backwards pointer has to equal to P, which they both have to be true to be, otherwise they're going to realize that there's some kind of corruption and just crash the program. There's more restrictions in the newer libc. I think it also checks to make sure that it's like a valid chunk, so there's a size at the beginning of the new chunk, and it also a size at the end of the new chunk, or the forward chunk or backward chunk. That was kind of a lot because backward pointer linked lists are always kind of hard to visualize. So hopefully when we go through this challenge, it should be a little bit more kind of clear cut. Let me close this. So today we have a challenge that was recommended to me for this from this GitHub link. It's from ZCTF, it's from 2016, so it's a little bit dated, but it's still a decent exploit for what we're kind of looking at. You could also probably go for a fast bin dupe by looking at how it kind of went. So I'll just run it quick to see what we're working with. So we'll be able to input our name, input an address, and then it's kind of just another note-taking system. So we have a new note, show note, edit, and delete, and then quit. So if we reverse this, go into this, we'll just start the beginning. Nothing looks too out of place. We have input name, then we have this function call, and it just looks like it calls read. So for now, we'll just call that read wrapper. Looks like input address, read wrapper. This might be the menu. Looks like it's menu, then it also reads in something. Read wrapper, then A to I, so this is probably just get int. Whoops. Then we have these functions, case 1, 2, 3, 4, 5, 6. And if we looked back, we have just new note, show note, edit, delete, and quit. So we just pretty much call them that just right off the bat. Let's call it create. This one will show. This one is edit. We had delete. There is a chance that maybe the jump table is different, but that would mean that these options wouldn't be accurate either. So there's no reason to really suspect that. So if we check out create, we can kind of walk through it. It looks like it checks this D word to see if it's equal to 3, so we can kind of summarize, or not summarize, but think that we can only create 3 chunks to allocate. And if we actually check it, it looks like it's only modified in edit and create, so it doesn't actually get decremented when we delete something, so we're only allowed 3 chunks throughout the whole thing. Input the length, it looks like we have another A to I, which I'm not sure why it called a different function. We'll just call this getInt also. Did I mess up the first one? So it was like A to L, I thought. Yeah, there's a get long too. Oh, this one calls getInt. Ah, okay. That'd be it. So it called getInt, and that just a getInt wrapper, I guess, is what I should have called the first one. But anyways, back to this. Looks like we can allocate a size up to 0x80 if it's below or equal. It's assigned comparison. So we can come down here, or unsigned comparison, so it doesn't matter if we put in a negative number or not. Come down here, it looks like it mallocs our chunk, puts, read wrapper, looks like it has a check or 10, but if we actually follow what's in RSI, it looks like RSI should be our size. We'll come back to that in a little bit after this function. So maybe we can just think that it's checking for new lines here, nothing else about it. Now we have the function here, which looks like it's a string length. It's looking for a percent. And it looks like it tries to either replace it or modify it. And since it's placing a 0 here, we can probably just call this function probably a format remover 3000. And then it kind of just does normal stuff, stores it back into the BSS so we can keep track of the chunk later. So here, let's check out read wrapper to see what it's actually doing. So it takes in our size. We'll just rename that quick. RDI is the buffer. Guess I can't name it buffer. Or just buff. EDX, EAX looks like what is called 0x0A for now. Can't call it that. Call it new line. Anyways, it only compares the new line character down here at this, where it actually, after it grabs the current character, it looks like. And it only reads in 1 character at a time. But another important thing to notice is this part, is that it reads in our size, subtracts it by 1, and then compares it before it even reads in any characters. So it looks like it's doing a decrement first kind of loop. And this could be problematic if there's no checks to make sure we go negative, which it doesn't look like there are. So if we pass in a size of 0, it looks like it should underflow into -1 and just keep going until apparently hits 0 or probably a new line, and then it'll return. But this allows us to pretty much just get infinite read in a chunk if we have a size of 0. which shouldn't matter because if we send in 0 to malloc, it should still return a minimum size chunk. So that looks like an exploit right there. Inside delete, jump if signed if compared to 0, so it has to be between 0 and 3. The pointer has to be allocated, freeze it, sets it back to 0, so nothing crazy there. Go to show, same thing with that, so no kind of out of bounds reads for us. Pointer looks the same as deletes, and it just printfs that, so that's probably what the, oh no, it does a format string, so I'm not really sure what the format remover 3000 was even for, but that's kind of up to them, I guess. And edit, test EAX, so maybe it checks to make sure we have a chunk allocated, because I think that's the pointer counter, or let's go allocation counter. Get the ID of note, compare it to 0, 3, make sure it's allocated by the looks of it, maybe that's the size, I'm guessing. Do you want to overwrite or append a 1 or 0? So if it's a 1, or it looks like it's a 1 or 2, not 1 or 0. Comes down here, but nothing really looks too different besides string copy first versus just setting the destination to 0. Then it looks like no matter what, it mallocs a size of 0, 5, 0. Adds this string to it, which it looks like the new contents. So maybe it's just adding kind of a verbal thing for you to see what you actually enter. Now that's actually just moving it into the new chunk. Then it's reading it on top of that chunk, it looks like. Yeah, this format remover grabs the string length of the current destination. So if we did a append, it'll take the current string length, string cat it, string copy, then free the malloc chunk that had this weird string in it. Nothing really out of the ordinary here. At first, it might kind of look like there might be a overflow here also, but between the string length and the string endcat, it takes care of your current size that it actually already took into account. I think it saves it right here. Yep. So it takes in your current size of your chunk, so you can't actually overflow at all. So there's nothing to really exploit here, but it's all in the create function, where if we send in a size of 0, we might be able to get something going with that. So since we're trying to copy the template to move exploit to E2, so I got the just template again as usual. Send, new, show, edit, delete with the process GDB. So since we're trying to get the malloc consolidate, we need to know a couple things. Malloc consolidate needs us to know a address of some sort that has a pointer to where our current data is, because we need to have the forward backward check be correct. So if we do a check sec on our note2, we can see that there's no pi. I'm not really sure why it's starting, why it's at 0x3fe, but as long as it actually shows up like that in GDB and the actual process, we shouldn't really care about it. Yeah, just interesting, I think. Guess I'm not really sure why it's doing that now. Maybe patch alpha is changing it after I patch it, but no worries. And since what I actually want to show you was that the checksec is off, so we actually kind of already have that pointer. So once we allocate a chunk, it gets placed into the BSS in this list, I'm guessing. So we do chunk list, and it's probably a 4 of them or something, maybe more than that. Maybe it doesn't even keep track of it correctly, or maybe it's up here. One of these is the actual pointer to the chunks that are allocated, so we can use that to create our unlink environment. So go back to exploit. First, we want to create 3 chunks. We want to create 3 chunks. First one, I'll go size 0x80. Yeah, 0x80. It doesn't really matter, I don't think, too much. A. The next one we'll want size of 0x. We want it to be allocated as 0x18 because, or allocated of 0x20 because that's the smallest chunk available. And this will be the chunk that we actually will attack with the kind of underflow with the malc from earlier that we talked about earlier. So if we delete index 1 and check that out in GDB, maybe. What are you hanging up on? Why? Maybe it was too large of a size. Go 7, 8. Now you're still hanging. Did I mess something up between this and... Why aren't you... Oh, no, that's right. Size, content. Debug time. Oh, not error. Wanted debug. Oh, gotta send it the name. That's why. That'll do it. So we'll do send at... we'll just send ASDF. We'll just do that twice, because we don't really care what's in there at the moment. Or at all, I don't think. Well, if we check out our heap bins after we freed that first chunk, we should see we have a fast bin chunk down here. Oops. So our next allocation of 0x20 should come from the fast bin, and that should allow us to overwrite the effective size of the chunk B. And that's exactly what we want. I think. Let me so I'm overwrite that I guess it's not really... We don't really want to overwrite the size of B. We more so want to overwrite the in-use bit, the previous in-use bit of B, because that'll cause the consolidation check when we actually free this chunk. So we delete 1. We can now do a new of 0 and then do P64. I think this should work because it's not, the read function isn't checking on these characters, it's only checking the new line, so I think we should be good to put this here. We want to put 2 because we want to make the previous size look a little bit larger than it actually was. So right now it looks like a size of 0x78. We're going to make it look like a size of 0x90. I think, let me do some mental math quick. It might be A0 actually. Plus P64 of 0x81, because that, no, not 81, 80, because we still want that to be the same size. And that should be good for that. Oops, plus. So go to the map to see what it actually looks like. So if we actually follow the parts, so when you actually free this, it's going to think that the previous chunk is freed, so it'll go back A0, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, what's 90? So right now, we don't really have a way to modify this value, because we only have 4 allocations, so we can't allocate a chunk before, like, kind of shift them all down 1 and allocate chunk before and do the same scenario we're doing here. What we actually have to do is put a fake looking chunk right here instead. And that's what we're going to do, is we're going to put a fake size right here of 0x70, no, 0x90, and change this to 90, wherever the A0 went. There it is. And then after, we're going to make it look like it's freed by putting in a potential unlinkable, or not unlinkable, but a realistic looking forward and backward pointer. And we're going to do that by setting the allocation pointer there instead. So we're at this 910, because that's the chunk it thinks it's at. So what we're going to want is this address right here, because we want the 10 bytes before, not 10 bytes, 0x10 bytes before. Let's call this address. Move this up here actually, and then change this up. P64 plus P64 of 0x91 plus P64 of address, and then P64 of address minus 8. Now, I'll explain this right after I go back into GDB, why we did the minus 8. So if we go back to the heap, not that one. So right now, this is where our fake chunk is looking. So if we free this, it'll try and consolidate backwards. So 20, 40, 60, 80, 90. So this all lines up. And then it's going to look at these forward and backward pointers because it currently thinks this chunk right here, this whole piece right here, is actually freed. So it's going to go to this address, the forward, and then check the backward, which looks like we're off by 10 because we want this to be backward, or 8. So we need to swap these two. But if this one is, pretend these two are swapped for now, and we're going to say this is the actual forward. So we're going to go to the forward and check the forwards backward to make sure it lines up, which it does. Then we're going to go to the backward and check the backwards forward to make sure it lines up, which it does. So since those both line up, it is then going to write this at this location and then this at this location also, since they both line up. And then since we just did our unlink attack, so now this allows us to have the BSS pointer inside our list, allowing us to just get arbitrary right on top of the list itself, and then from there we can just get an easy exploit going. So we're going to need to fix that before we continue. Do minus 8 here, and then minus 8, plus 8 I guess. And then we can check. I'm just going to have you guys believe me that it's that way, and then just do a quick delete of note 2. Check our heap bins. We can see that this shouldn't be here. Did I mess something up? Oh, it's a fast bin. Yes, that would cause a problem. So, since that is technically a fast bin size, we're actually going to need to go one size up, because since it was put in the fast bin, it's not going to be consolidated or technically fully freed, in my opinion. But we should be able to fix that just by changing this to an 8-0. Then it should be a chunk of 0x90 technically, which breaks if we change it back to 80 down here. So we continue, delete the note, and we check the heap bins. Nothing there, nothing in the unsorted bin. And if we actually check the actual heap, we can see that the top chunk size is actually up here now. So that means this whole chunk is looking like it's freed. And if we go check out our BSS value, we can see that we got our overwrite that we wanted right here. So now we have a BSS value which points straight before itself right here and allows us to overwrite when we get our if we edit it. And that's all we really need to do to show it. So edit index 0. We'll do an overwrite because there's nothing really to concatenate to at the moment. And we'll just put in a bunch of A's. Heap bin, no, not heap bins. Go back to this spot, and we can see that in fact we did just overwrite everything, which at this point means we kind of killed our entire process because we don't control this memory address. But this is just a show. So now we need to figure out kind of where our best approach would be, and are there any suggestions on methods that we should use for this next, or for the final exploitation, get the shell. Okay, great.
Overrate a hook.
ROP.
Yep.
Dude, I have no idea.
We could do a ROP chain. Did you want me to do ROP?
Would overwriting
What's the other one?
Would overwriting like free hook work? Is there an unlink hook?
Free hook could work, but I think we should. That one actually might be difficult. So the ROP might be difficult also because the ROP would be easier, I think. because we're only allowed, since we're editing, if we go back to it, it does this string length string copy after it reads it into this fake malloc chunk first, which we never actually look to see what it actually looks like. Just do a little note. New note 24 doesn't matter. Edit 0. We'll go all B's. Whoops. Go overwrite. This is what it mallocs first, is this part, and then it'll move our data over to our actual thing. So since it's using string copy, we're not allowed to put null bytes, so which means we kind of only have one shot at this in a sense, because we're not allowed to modify more than one chunk pointer. I think I need to delete it still. So right here, once we actually start editing this, we're only allowed to get up to here, because once we try to put an address here, we get killed off once we put our first null byte in, and it's not allowed us to put another piece. So if we put this to free hook, we wouldn't be able to, I guess if we knew the address of free hook, we'd be able to put it there and then get it going, but we need a way to leak it first before we could put it to free hook. But the ROP could work, because we could edit a ROP chain into this location, and then maybe if there was a gadget that allowed us, inside the binary, allowed us to gain control of RSP, and we overwrote something in the GOT to do that. But the way we're going to do it, because those both sound like more difficulty than we really need to do, is that we have this address of A to I, and we know that A to I is used in a bunch of places as the get int, and we can control what gets sent to the get int, or not get sent to the get int, but what gets sent to A to I by sending whatever data we want, because that's the first thing that's read when we do this part. So if we overwrote A to I on the GOT to system, then we just have instant control and are able to run whatever we want on the system. So
Yeah, let's do that.
That sounds much better.
So let's grab A to I's address. That we can delete 2. We'll edit 0 with 1 just to say we're going to overwrite it. We'll do, can't do any null bytes, so let's do that times 0x18 plus p64 of A to I underscore got. I think that should be good.
Missed the plus sign.
Yep. And then from there, we should be able to do a show of 0 and see what we have. So if we look, we have the effective leak, and if we do a GOT, we can see that 80 E9 or 9E valid character, 33 is another valid character, but yeah. Oh wait, no, 33, 3E, oh 3, okay, yeah. That's right. So while we're here, we're able to leak this, so we just have to read until is space, and then read to a new line, and then we have the leak. So we'll just take this quick and find the address of system off of it. Do system minus A to I, because we don't really care about any of the other addresses. Save that quick, equals leak minus that. Then we do a p dot read until is space leak is equal to p dot read until new line. Get rid of the new line, and then leak is equal to u64 to unpack it. Left adjust it to 8 characters because Pwn Tools can't figure out it on its own for some reason, because I'm unpacking a 64 byte, but whatever. And we'll change this to system. All that's left is to edit 0 one more time with the address of system now. And with that, we should have a fail. Nice. I didn't swap those two, I don't think. Maybe I did? Yep, I did. check our GOT. That looks like a different address, just to make sure it's the address of system. We can see that it actually isn't, so maybe that isn't a different address. Maybe that's actually A to I.
It looks different.
It does look different, but that's not the address of system. I think I did a subtraction when I want to do an addition. That might have done it. That looks better, I think. Yeah. Alright, that looks like system. So, all from there we need to do is just send in bin sh, and we have a shell. And then the beauty of this is that we can, if our shell were to accidentally die, we're still technically in the application. So we just need to run bin sh again, and we have another shell. There's no, I don't think there's any way to actually exit out of this process cleanly anymore. We just had to kill our connection because we can't send in any numbers. If we were to possibly overwrite a different function inside, like create or delete, maybe if we overwrote free and just kept, no, because that would have set our thing to 0 after we freed it, so we wouldn't be able to free it again. There's not really any great spots to get a clean exit, but we don't really care about a clean exit in this kind of scenario. It's just mostly get the shell, get the flag, get out. But yeah, that was the exploit for that. Are there any questions?
How'd you get the leak again? I'm
So,
slow.
since the binary didn't have pi enabled, so the address was always at the same spot, we're able
Yeah.
to overwrite the first item on our the first item, gosh, we're able to use the unlink to overwrite the first item in the list, so index 0 of our allocation list, right?
Sure.
So here's the allocation list, and currently index 0 points to the value right before it. So if we overwrite this to be a pointer to the GOT, I guess it's the same address every time, I should know that. So this address now index 0 now points to A to I, and we're able to just show that based on just the application itself. So if we show index 0, it now prints out the address
Okay.
that's stored at the A to I GOT value.
Heard.
So that's how we got
Thank
it
you very
over.
much.
Yeah.
Now if pi was enabled, you would probably be out of luck, I think, with this current application because we just don't have enough allocations. You'd still be able to leak probably the heap and then maybe get something from there because you should be able to leak libc from heap. But you won't be able to get enough allocations to actually pivot anywhere useful, and that's the main problem with that. But overall, the unsafe unlink technique isn't really used as much anymore. It's still possible, but there's just more restrictions, mostly that I think the chunks had to be valid sizes, which for this application we could have done because our name is set right here, and then our address is set down here, so we're actually able to get somewhere right here. So we could make this look like a valid chunk, and that's where the fast bin technique I think could come in. Fast bin dupe. So if we made this look like a valid 0x80 chunk, and another valid 0x whatever size chunk down here, we could put in a fast bin dupe right here and pretty much get the same, just another address in there also, I think. But yeah, that's
Wow.
exploitation for today. Thanks for coming and for watching.